Good morning, stats scholars. I'm sorry I'm not on campus today. I have a really nasty migraine, but I'd like to go through the notes for today. So we're going to go ahead and jump into note 6C, where we're going to be talking about the other type of inference that we can do in statistics. So far we've estimated unknown population values using a confidence interval. Now we're going to learn how to test claims made about a population. And that's called a significance test. So significance tests are used to test the validity of a claim made by somebody else about a population. In confidence intervals, we use the sample data to construct the interval. The sample statistic became the center, and then we used the standard error of the sampling distribution to determine the width of that interval. In a significance test, which is called a hypothesis test, we already have a population value. The sample's then been used to determine whether that statement is likely to be true or not. We also call significance tests hypothesis tests. You'll see those two phrases used interchangeably. And hypothesis tests use sample data to decide between two competing claims. And those claims are called hypotheses, which is sometimes why these are called hypothesis tests. The first claim is called the null hypothesis. And you'll notice the symbol H with a sub-zero beneath it. This is the claim that we weigh evidence against. We're either going to reject this claim or not reject this claim. This is a statement of equality. Typically in the problem, we're given a population value. This statement is that the population value is equal to whatever we were given. We are assuming that that value we were given is true. We are going to write these statements strictly as equality. If you take stats again, some statisticians will use a less than or equal to or a greater than or equal to, so that when you look at the other type of hypothesis, which we're going to look at in just a second, the two symbols here complement each other, meaning they cover the whole number line. Because the structure of our test only depends on the second statement, it doesn't really matter whether I use an equal sign or a less than or equal or a greater than or equal, which is why most statisticians, myself included, just default to equal. Because as I mentioned before, statisticians are lazy. The competing claim, the one we are trying to find evidence for, is called the alternative hypothesis. This is always a statement of inequality, not equal to, greater than, or less than. The structure of the alternative hypothesis determines the structure of our test. So this is where that symbol matters. This claim also determines whether our test is one-tailed, meaning less than or greater than. I only care if my sample is less than the stated population value or greater than the population value. Or it can be two-tailed, meaning I'm asking the question, is the actual value different from the stated value? And different could be less than or greater than, and so we get a tail on both sides. we're going to practice setting up these hypothesis statements, and then we're going to look at a couple other moving pieces of hypothesis tests in general today. When I see you next week, we'll specifically go over what this looks like for population parameters, just like we did for confidence intervals. So when you write out hypotheses for a significance test, those symbols, HO and HA, are labels. The competing claims about the population parameter then follow those statements of equality and inequality. You should never have HO equals or HA equals. Let's go ahead and do 2 examples so we can see what that looks like. So example 1 says James is a manager at the Hawaii Pineapple Company and is interested in the size of pineapples grown in the company's fields. Last year, the mean weight of pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in this field after growing season. James wonders if this change will affect the mean weight of pineapples grown in the field this year. State the appropriate hypotheses for performing a significance test. Be sure to define the parameter of interest. So picking through that word problem, the first thing I see is last year, mean weight, 31 ounces. So I know that I'm testing a claim about a mean and that the claimed value is 31 ounces. As we keep reading, it says different irrigation system. James wonders if this change will affect the mean weight. But notice when he says will affect, he doesn't say will increase or will decrease. That tells me that James is just interested in a change. And when we're just interested in a change, our alternative hypothesis becomes a not equal to question. So we're going to do 3 things. We need to define our population parameter, which is weight, a mean weight. We know population means are mu. So this is the population mean weight of pineapples for the Hawaiian Pineapple Company. And then I want to define my hypotheses. So first I'm going to write my labels, HO, HA, with colons. Then I am going to make the statements about the population parameter. So the claim is the mean is equal to 31 ounces. That was the statement that was made from last year. It was 31 ounces. We're assuming it's still 31 ounces. James wants to know if that value has changed. So my alternative is going to be not equal to, different from 31 ounces. And you'll notice a couple of things. The equal sign comes after the population parameter, not after the hypothesis label. These are labels. These are the actual equation components. The other thing you'll notice, there's a population value, or population parameter, sorry, I can't talk today, and then the value that goes with it. At no point did I need sample data to do this, because hypothesis testing has to do with testing claims about a population. I need sample data to do that, but in terms of the setup for the test, I'm interested in those statements about the population. I'd encourage you to pause the video for just a second and try this one on your own, but we're going to go ahead and do another example. So it says, axe throwing has become a popular recreational activity. Your friend claims to hit the bullseye on 2/3 of their throws. You doubt your friend is as accurate as they claim. State appropriate hypotheses for performing a significance test. Be sure to define the parameter of interest. So in this problem, claims to hit the bullseye on 2/3 of their throws. And 2/3 is a fraction or a percentage, about 67%, which means this is a claim about a proportion. So I know that I'm going to need to define my proportion. And this is the population proportion of center hits on the bullseye. Then we make our statements, our hypotheses, the null hypothesis, the alternative hypothesis. Because this is a claim about proportions, I'm going to have P equals and then P and then an inequality, which we'll deal with in a second. And we're told the population claim value is 2/3. The friend is stating, I can do this 2/3 of the time. So 2/3 or 0.667. What comes after that is your friend doubts they're as accurate as they claim, meaning your friend thinks that they're less accurate than they're stating. So this would be a less than test. Not 2/2, 2/3. This can be a little bit intimidating as we get into this, because again, this is going to determine what our test looks like. On the FRQs for the AP test, if you get this wrong, but everything else you do after that matches what you stated here, that's mostly correct, and they will give you most of the points. So it's more important that you understand the connection between the symbol in your alternative and what comes after than correctly interpreting the word problem. That's an important piece too, but in terms of point deduction, I don't want that to be something that causes you to panic. Okay, so again, reminder that we're testing claims about populations, so we should not have any information about our sample data in these hypothesis statements. That's a really common mistake that I see when I teach stats. Okay, so far we've set up the claims about the population we want to compare and test. And the question is, how do we do that? And the answer is we look at our sample data. And we're answering the question, how likely is it that I get a sample like the one that I did, assuming that the null hypothesis is true? The probability that I get a sample as extreme as the one I did or more extreme is called the p-value. So the p-value is the probability of getting evidence for the alternative hypothesis, HA, as strong or stronger than the observed evidence, which comes from our sample, assuming that the null hypothesis, HO, is true. What that means is when we build our sampling distribution and we start looking at probability using normal CDF, the center of our normal distribution is going to be the value that we stated in HO. We are going to assume that that is the center of the distribution. And then we're going to look at how likely it is that we get a sample like the one that we did, assuming that that is true. What we're going to do now is practice interpreting that p-value so that we can understand how to make conclusions. So example says calcium is a vital nutrient for healthy bones and teeth. The National Institutes of Health recommend a calcium intake of 1,300 milligrams per day for teenagers. The NIH is concerned that teenagers aren't getting enough calcium on average. Is this true? Researchers decide to perform a test of the hypotheses the mean is equal to 1,300 milligrams versus the mean is less than 1,300 milligrams, where mu is the population mean daily calcium intake for teenagers. They ask a random sample of 20 teens to record their food and drink consumption for 1 day. The researchers then compute the calcium intake for each teen. Data analysis reveals that the sample mean is 1,198 milligrams with a standard deviation of 411 milligrams. Researchers performed a significance test and obtained a p-value of 0.1405. And the first thing we're asked to do is explain what it would mean for the null hypothesis to be true. So going back to our null hypothesis, that's this guy here. If the null hypothesis is true, that means the population mean calcium intake for teenagers is actually 1,300 milligrams per day. Our evidence for the alternative comes from the sample. So looking in the word problem towards the end, I see an X bar value. X bar is our sample mean. So the, not same sample, come on, Mr. J. So the sample mean calcium intake was 1,198 milligrams, which is less than the stated 1,300. So I can see that my sample is leaning in that direction. It is certainly less than. The question is, based on that standard deviation and what we know about the spread of the population data, is this value within about 2 standard deviations of the stated value? Because if this is within approximately 2 standard deviations of the stated value, it's possible to get this and have this statement still be true. If this is way, way out in the tail, more than about 2 standard deviations away from the mean, then this statement is no longer likely true. Our sample is providing evidence against that. So let's go look at our p-value. It says interpret our p-value. So our p-value is 0.1405. So what that means is, assuming that the actual mean is 1,300 milligrams, there is a 14.05% chance, chance, that a random sample of 20 teens would have a mean of, and what did we have, 1198, or, and in this case, more extreme means more in that direction, so 1198 or less. So assuming that the population value is actually 1,300 milligrams per day, about 14.05% of the time when I collect a random sample of 20 teens, I'm going to get a sample mean of 1198 or less. What that tells me as a statistician is this value is not that unlikely, meaning I'm disinclined to reject the null. This is still quite reasonably true. This one sample of 20 teens having a value that's 1198 is not enough evidence for me to reject that null. Good, so pause the video for just a second. I want you to try that same process for example 4. So example 4 says the Pew Research Center asked a random sample of US parents if they knew their child's cell phone password. Of the 1,060 parents surveyed, 52% reported they knew the password. Does this sample give convincing evidence that more than half of all parents know their child's cell phone's password? A significance test was performed of p equals 0.5 versus p is greater than 0.5, where p is the proportion of all US parents who know their child's cell phone password. The p-value for the test is 0.0985. And the first thing they ask is, explain what it would mean for the null hypothesis to be true. So our null hypothesis, that's the first statement, the statement of equality, is p would actually be, not by, be 50%. Meaning 50% of US parents knew their child's cell phone password. And we define P in the word problem up here, so I'm not going to be nitpicky about using it when I'm talking. Next, it says state the evidence for the alternative, and the evidence for us is the sample data, which is up here. In a sample of 1,060 parents, 52% reported they knew the password. So our sample proportion p hat is 0.52. And then it says interpret the p-value. So our p-value is down here. And that's measuring a probability. So assuming that p actually equals 0.5, there is a 9.85% chance of selecting an SRS of, what was it, 1060 parents, where 52%, and remember it's equal to our sample or more extreme, and in this case our alternative is a greater than statement, so more extreme would mean bigger, where 52% or more know their child's password. And we'll notice in this example, that probability is less than it was in the last example, but that's still pretty big. I'm not way out in a tail, because I know that if I'm at a 90% confidence, that's 5% in each tail. This is more than 5%. I am likely within 2 standard deviations of the mean. That's not an extreme sample. So I, as a statistician, am not confident enough to say that that one sample with a percentage of 52 is enough for me to reject the statement that the proportion is actually 50. I would need something bigger than 52 in this case. No, I didn't mean to do that, sorry. Okay, so the question is, now that I know what a p-value is, how do I make a firm statement about whether that p-value is enough to reject the null or not reject the null? And the answer is, we have something equivalent to a confidence level for significance tests, and that's called a significance level. So the significance level is the value that we use as a boundary to decide if an observed result is likely or unlikely to happen by chance alone, assuming the null hypothesis is true. If the p-value is less than or equal to our level of significance, we reject the null, because that means that the probability that I get my sample, assuming that the null is true, is unlikely. Because this is the boundary where I've set. If I'm more extreme than this, that null is likely not true. If my p-value is less than that, it means I'm further out in that tail, meaning my sample is even more extreme than the cutoff for rejection. If I reject the null, that means we do have convincing evidence to support the alternative. So up here, for example, in example 4, if my level of significance was 0.10, notice that this p-value is less than 0.10. And I would, in that case, say I would reject the null and I support the alternative, because my sample is more extreme than that cutoff for reasonable data. If, on the other hand, my p-value is greater than my level of significance, we fail to reject the null. In this case, that means that it's somewhat likely to get samples like ours, assuming that the null is true. And that means we do not have convincing evidence for the alternative. You'll notice here that both of these bullet points make two statements, one about the null, one about the alternative. We're going to see that pattern in our conclude step when we're performing significance tests. Anytime we make a conclusion for a significance test after we've made our decision up here, we're going to write two sentences. The first, this part up here, addresses the null. The second sentence addresses the alternative. And you should always write both. So let's take a look at what those sentences can look like. So the first says, because the p-value of, and then we're going to put our number in here, whatever we calculated our p-value to be, is less than or equal to alpha equals, we put our level of significance here, we reject the null hypothesis. There is convincing evidence for, and then in this blank here, we're going to write the alternative hypothesis in context. So there is convincing evidence for the claim that the population proportion of parents who know their students' cell phone password is greater than 0.5. If our p-value is greater than our level of significance, and we plug those numbers in, we fail to reject the null, and there is not convincing evidence for the alternative hypothesis. So, important to note, reject the null means is convincing evidence. Failing to reject the null means not convincing evidence. In your head for testing, we need to have those two things connected because they're going to be checking that your two conclusion sentences are consistent with each other. And that is a really common mistake that I saw particularly last year. So if we reject the null, we do support the alternative. If we fail to reject the null, we do not support the alternative. So reject is evidence, fail to reject, not evidence. Before we do some examples, I want to give you one more warning. This is super important, and I see a handful of people do it every year, and it makes me sad. When we are talking about hypotheses, we are talking about statistical tests, we are always talking about likely to be true or unlikely to be true. We cannot make a definitive statement based on one sample about whether something is fact or not. So when you are writing your conclusions, when you are discussing hypothesis testing and the results, you should never use the phrases true or correct. If I see those on your assignment, I am going to deduct points. That is a big fat no-no, and I see it every year. And not just with the high schoolers. I see it when I teach college stats too. It is tempting to write true and correct when we're drawing conclusions. We cannot do that in statistics. I can make a statement about whether something is unlikely or likely, but I cannot state something is fact or not fact. That's a different level of certainty than what we're doing here. If you stick to your sentence frames, that won't be a concern. So again, I would encourage flashcards for sentence frames so that you don't have to worry about that particular issue. Okay, so just two quick examples, and then we will be done. Yay. So it says, in example 3, researchers collected data, daily calcium. We read all of that. Said p-value was 0.1405. What conclusion would you make at the alpha equals 0.05 level? Meaning I'm saying that 95% of the data is 1300 or greater. There's a 5% that's less than. If I'm out past that 5% in the tail, I'm frowny face. So we're going to compare, one of those C words, the p-value to the significance level. So p-value, significance level. And I'm going to scroll back up. And what I'm looking for is it less than or equal to, or is it greater than that level of significance? Meaning, am I way out in the tail? Am I an extreme sample? Or am I closer to the middle and I'm not an extreme sample? So we're going to make a statement. I know my p value is 0.1405. I know my alpha is 0.05. My p-value, 0.1, is greater than my alpha of 0.05 because when I compare, I do it by decimal place. So 1405.05. Starting with the tenths place, p-value's got a 1, alpha's got a 0, so p-value's greater. Once I've figured that out, I just go up to my sentence frames. P-value's greater than alpha. I write my sentence. So, because the p-val of, and then I write my number, 1405, is greater than alpha equals 0.05, we fail to reject the null hypothesis. There is, and if I fail to reject, there is not convincing evidence for the claim that, and then I go back and look at what my alternative was in the problem, and we're talking about daily calcium intake. So there is not convincing evidence for the claim that the daily calcium intake for teens is less than 1,300 milligrams. And again, three moving pieces: p-val, alpha, the statement of the claim or alternative claim in words in context of the problem. Again, we see that pattern. So we see fail to reject, not convincing evidence. Those two go together. Take a second, pause the video, and try the next one on your own. And then you come back and we'll do it together. So last example says Harris poll found 33% of US residents believe that finding and picking up a penny is good luck. Mr. Tyson suspects that the students at his school are more superstitious than the nation and wishes to perform a test of p equals 0.33 versus p is greater than 0.33, where p equals the population proportion of students at Mr. Tyson's school who believe finding and picking up a penny is good luck. From an SRS of 100 students, he finds 45 who believe finding and picking up a penny is good luck. The resulting p-value is 0.0054. What conclusion would you make at alpha equals 0.10? So p-value, alpha, my definition of the proportion that I'm talking about, and then my alternative statement, which is that p-value is greater than 0.33. So we'll do a quick comparison. We want p-val versus alpha, and in this case our p-val is small, 0.0054, and our alpha is big, 0.10. So again, we compare by decimal places. The p-value, the tenths place, is a 0. The alpha, the tenths place, is a 1. So alpha is greater than the p-value. If I scroll back up, p-value is less than or equal to alpha, we reject the null. As my students last year said, if p-value is low, reject HO. So our p-value is low, we're going to reject HO. So because the p-val of 0.0054 is less than alpha equals 0.10, we reject HO. So that's the first sentence, making a statement about the decision for the null. And then we make the statement about the alternative. Since we reject the null, there is convincing evidence for the alternative. So there is convincing evidence that more than 33% of students at Mr. Tyson's school, oh, this is a lot of writing, believe finding and picking up a penny is good luck, because I'm going to run out of space. We see those same moving pieces, stating my p-value, stating my alpha, stating the claim in words, stating that alternative in words. And again, we see that connection between we did reject and there is evidence. All right, if you have any questions, you can reach me via email. Otherwise, I will see you on Monday. When I see you on Monday, we're going to take this idea and apply it specifically to proportions. I hope you all have a great weekend, and I'll see you on Monday.